Good afternoon, everyone. I, Arpita, with my friend Shubhasri, welcome you all again to Atal's FTP 2021. We are already in the second technical session of the day, so without wasting any of our time, let's take forward this event. This session's topic is application of AI and ML for visual surveillance. For this discussion, we have with us one of the eminent speakers from IIT Bhubaneswar. He has a brilliant career with a PhD in computer science and engineering from IIT Kharagpur. Also, he has completed his MTech in computer science and engineering from IIT Kanpur. Speaking of his professional career, currently he is working as an assistant professor at School of Electrical Sciences, IIT Bhubaneswar. Before that, he has worked as development manager at Samsung Research Institute, Noida. Also, he had been a researcher at Electronics and Telecommunication Research Institute, South Korea. He had privileged us by accepting our invitation again this year in a row, as we all CETians can remember him addressing us all last year during the FDP on smart medical services. He is none other than our very well-known Professor Debi Dogra sir. I guess I need not say any more. I'll directly request Dr. Debi Dogra sir to take over the session. Over to you, sir.
Good afternoon, Dr. Mahapatra. Am I audible?
Yes, sir.
Okay.
Yes, sir.
So, is my screen visible to all of you?
Yes, sir. Completely visible.
Okay, great. So, thank you for inviting me to this FDP. So, the topic of today's discussion is on applications of AI and machine learning for visual surveillance. And I shall be primarily discussing the latest research work that are being carried out into this field, and obviously starting with some of the preliminary things, okay, to understand that what is visual surveillance and how AI and machine learning has actually helped to achieve certain goals which were not earlier possible into the domain of visual surveillance. So if you have any query, you can note those queries and we can discuss during the QA sessions, or you can also ask me in the middle if you have any immediate query, or we can also take up the discussions toward the end. Now, let us try to understand that what is computer vision and visual surveillance. If we define computer vision academically, it says that it's basically the science and technology of machines that see. We are concerned with the theory for building artificial systems that obtain information from images. Now, what kind of images? Images the image data can take many forms, such as it can be a video or a sequence of images. It can be depth images. We can have recordings from multiple cameras, or maybe a multi-dimensional data from a medical scanner like a CT scanner or MRI and other similar medical equipment devices. And we all we can capture these data, and they are stored in different formats. The objective is to understand these images and try to semantically define that what these images contain. Like we humans, we actually do it. Just by seeing an image, we say that this image contains XYZ objects. Similarly, we want a computer to do that. So that's why computer vision actually talks about understanding the image. When you talk about visual surveillance, so we want automatic systems or maybe artificial intelligence guided systems that can actually replace the human actor in the system, in the loop. So the surveillance, in a sense that we want to observe something for a continuous period, and whenever sudden change is there, we would like to flag it so that the actions can be taken. Sometimes we may need to take corrective action. Sometimes we may need to enrich our knowledge also. But that's why surveillance is needed. I'll tell you that what are the different applications today throughout the whole presentation today, and I hope that you will find these examples interesting, and I'll try to discuss as much as possible that what are the underlying techniques behind these applications. Now let us start with a very simplistic, pictorial depiction. That when we say that what kind of answers we want from a computer, given an image like this. Okay. So what do we want? We want to make computers understand images and videos. Let's take this example. You can actually generate hundreds of questions out of this image, starting from where is the car, how many trees are there, what is the color of the car, how many cars are there, which car is far away from the camera. Okay, so what is the type of the scene? I mean to say that you can come up with thousands of such questions, and each and every question will be having its own different answer, maybe having different answer. So since a particular image or scene can actually generate such hundreds or thousands of questions, you can understand the complexity of the problem. It's not like that we are able to answer all these questions. We humans are able to answer all these questions just because in one day. We learned all these things maybe throughout our lifespan. We learn every day. Something we don't know, our teachers help us to understand. Our parents, guardians, or our friends, whoever with us, they actually help us to understand. So this learning process is going on. Even sometimes our past experience also helps us to understand. Now this learning is a continuous process. We don't say that we are not learning from this day onwards. We learn. Now the questions which may be framed out of this particular image, we might have learned all such questions because we might have seen similar images. Okay, and we know that how to basically frame the questions from a given set of objects and their relations, spatial relations. So when I talk about spatial relations, that means which object is present where and how they are located within the image. What is the relation, semantic relation? So that's why it may be easy for us, but if you would like to do it for a computer, we need to understand that what are the preliminary tasks. Okay. So a question can be what kind of scene. If you would like to answer this question, what kind of scene, what you need to do, you need to understand what are the objects. Now let's take this big picture. What are the different objects available? Here are car objects, trees, maybe cloud, a building, chimney. I mean to say that flower pots. There are so many other objects also. Now, if you want a computer to automatically recognize these objects, you should ensure that the computer is well trained. So we need to provide some sort of training. So that is what is more complex. We are learning, we humans, we learn every day, and we are learning our learning never stops unless we sleep or we are in a different state of mind. We always learn. And this, so when we are learning our model, whatever we call it, physical neural network model, which is with us, it's continuously getting updated. So similarly, for a computer also, even if you come up with a model, artificial neural network based model, or something else based model, it needs to learn. Okay, and you need to provide a lot of evidence so that the system can learn. So now, when we provide evidence, what do we mean by evidence? Evidence means when you want your computer to learn about trees, you need to provide maybe several tree samples captured from different angles, because you do not know that in the testing time from which angle you will be able to see the tree. Ideally, you can see it from any angle of 360 degree, but it may not be possible to generate all such samples, but you can still generate a lot of samples and provide it to the system as training data. Now, question here is that if we provide this training data as raw, like simple image, how computer is going to remember all these things? So obviously there are certain intermediate steps that we need to do. We need to extract features, those features which can actually be represented in a mathematical form and which can be used by a computer or an algorithm, which we call maybe a typical classifier, which can actually, depending on the features of the current input, it can take a decision based on a trained model. Okay, so the process itself, why I'm saying all these things, because it's not that easy that we do it everyday life. Okay. So questions like what kind of scene requires how many objects are there and their spatial relations, and then even if there's, why I'm talking about spatial relations, because these spatial relations may define the characteristics of the scene even if the objects are similar. Even if the objects are similar. Like lots of cars inside a building can lead to a showroom, conclusion of a showroom. But if lots of cars also with a building, maybe it's maybe a parking lot. So why I'm talking about spatial relations, whether the cars are within the building or outside the building, this is basically spatial relation. So that decides that what kind of scene, whether it is a parking lot or whether it is a car showroom. So that's why it is very important, not only that the detection of the object, how they are related, that is also very important. So somebody may ask that where are the cars? A different question can be, where are the cars? So when you try to answer this question, where are the cars, you need to understand that these cars should be, the position of the car should be defined with respect to some other objects. Again, there will be some spatial relations coming with respect to any other objects. Another question can be, how far is the building? So how far is the building? So this can be answered in many ways. It can be 100 meters from the camera, it can be 200 meters, it can be far away from other objects. The answers can be also can be subjective in nature. If you ask the same question to 5 human beings, you may get 5 different answers and all may be valid. So the reasoning given by each and every user may vary. That's why it is really a complex problem. Now, what are the components of a typical visual surveillance system? We see that we have a camera, obviously, because that's a sensor which actually captures the scene. Then we have the scene where the objects are present. We must have a computer which is connected with the camera. It may be wired connection, wireless connection. Okay. But that is the brain, where basically the signal gets processed and you take a decision. So the scene representation actually happens within the computer. So these are three components which are very important for a typical to build a typical surveillance system. Now, if you look into it, how it is varying in human vision and computer vision, what we see the left side is basically it's an image, and that is actually what we see. Whereas if you take a look into the right side, which is nothing but an array of numbers, two-dimensional array of numbers arranged in a particular order, this is what a computer sees. Now, as a computer vision scientist or a visual surveillance expert, what you need to do, you need to basically represent this array of numbers in such a way that you can find a mapping between what we see and what the numbers are. So that finding a good match, good mapping is very important. So there can be several mathematical models to map these things, like how to represent the train engine which is being shown in the image, which portion of the raw data actually describes that the train engine is there and the ladders are there, something like that. I mean, so that this sort of mapping has to be there. Okay. So that's why it is really complex. If you look into the right side, we have only numbers. Here I'm presenting you the decimal digits. Actually, these are binary numbers. Okay. So binary numbers means it's only 0 and 1, sequence of zeros and ones. Okay. So it's really challenging to map these 0 and 1s, a block of zeros and ones, to some area of the image. So it's really a hard problem. So it's an amazing feat of natural intelligence. If you look into it, the portion of our brain that is occupied by visual cortex is huge. I mean to say that for a typical macaw brain, it's 50%. Okay. So we can easily say that more human brain devoted to vision than anything else. It's really hard. So when you take decisions like that, is that a queen or a bishop? After your careful observation in the scene, you only take it. That other careful observation, you have not learned these things in one day. You might have seen these chessboards several times in different formats, in different ways. While maybe you were watching TV, you have also seen chessboards. While reading newspapers, you might have seen chessboards. While actually playing chess, you might have seen chessboard. There are many scenarios where you have actually gone through this chessboard and you have seen these chessboards from different angles, from different perspectives. Okay, so if you look into the same object from a different perspective, it will create a different type of image in your brain. But the object does not change. The physical object does not change. So the same object is being seen from 10 different angles. They actually map to the same mathematical model, which I should actually link it. So that's why it is difficult. So how many possible such variations, for infinite possibilities are there to see an object? Okay, infinite possibilities are there. You can see an object from infinite perspectives, changing the position, the camera. You can have infinite positions. Even if it is a 360 view, you can change in a typical decimal point, you can change it. So okay, you can understand that it can be placed in finite positions. Even if you have finite, then it's a large number. If you define the finite positions, it's a large number. Now, when you see that object from this set of these positions, the images which are created are different. I mean to say that not necessarily always different, but you may get strikingly different perspective. But the object does not change. So the challenge is you need to ensure that all these images of the same object map to the same mathematical model. That's why it is challenging. Maybe by God gifted, we have the vision, and it's an amazing feat of natural intelligence. So how it is working, it's still a question. I mean to say that how complex the system is. And obviously, it is multidisciplinary. It requires the knowledge of, many other domains. You require knowledge of artificial intelligence, machine learning, mathematics, neurobiology, imaging, basics of imaging, signal processing. If you would like to develop applications, you may require knowledge on control robotics. Okay. You may require, you need computer graphics. Okay. So these are allied subjects which are needed. Obviously, one person may not be an expert in all these subjects, but you can actually take up your interest area and take the help of others or existing techniques and come up with a solution, because knowing all these subdomains may be difficult for one person. But why it is needed then? Surveillance and computer vision is needed. It is needed for various applications. Like I already had a talk earlier with CET on mainly focusing on healthcare, how vision is used in healthcare. Today I will be mainly focusing on surveillance. I will tell you that how it is different. So it can be used for safety purpose, it can be used for healthcare, it can be used for security, it can be used for typical gaming, comfort, fun, ease of access. Okay. There are other applications also. Industrial applications, I will also show you that how industrial applications are there. There are lots of industrial applications. So how it has evolved. It has started all during the 1960s, started in MIT. They have actually started some project to link a camera with a computer and getting the computer to describe what it saw. You can understand that in the 60s, when the computer itself was not easily available, it was in the form of, not in the form of semiconductors, it was in the form of tubes, vacuum tubes. Okay, you can understand how difficult it was there. But people actually thought about it because the problem was there. Maybe the equipments were not available, but the problem was there. Okay. So if you look into the chronology, you will find something like this. Okay. So in the 70s, you will find that some progress on interpreting selected images. Selected images in a sense, I mean to say, it will not be able to process any kind of image. It will be able to process maybe black and white image with some restrictions. Okay. Then the methods like age detection came. Okay. Artificial neural networks, they came not recently, they came earlier, 1980s ANN came in. Okay. Because, why it went? Because the kind of computations required to use artificial neural network for solving computer vision was not affordable at that time. So people, even though wanted to, they knew that what are the techniques, or I mean, what are the mathematics behind artificial neural network, but they could not pursue it or apply it because the resource was not available. Some applications came in 90s like face recognition, statistical analysis involved. Okay, these things, they were still not based on neural network based applications. They were mainly based on handcrafted feature things. And as we moved to the new millennium, okay, so we went for broader recognition. The large annotated databases were available, and the video processing starts. So all the vision, graphics, computer vision, HCI, internet vision, everything came. The new millennium. That's because, not only because that we suddenly came to know about the theory. No, theory was there, but because of the advancement in the semiconductor technology, we were able to create hardware systems that can process a lot of information together, like the typical SIMD processors, single instruction multiple data processors, array processors actually they started to arrive, and that actually helped. And then we got the GPUs, which are smaller units but in large numbers. They do the similar operations. They don't do generic operations. They do only specific operation, maybe a convolution operation, multiplication operation, but they do in parallel. That means you have many such units available in a chip, so which can actually process the whole image at a time. So that's the advantage. Okay. Which earlier it was not possible because the hardware was not supporting them. Theory was there. So now I'll show you how actually vision is used with some examples of the state of the art. So let's see. This is probably the oldest of the work, which you can see that AT&T actually came with one application where they recognize the digits. Okay, so they recognize the digits, and you'll find that sometimes they are able to answer the correctly find out what is the digit. Sometimes they are not able to find the digits. Okay, but later on, there are many advanced techniques came, and it was able to even recognize these digits with highly accurate systems. How it is used? It can be used for say number plate, license plate detection kind of thing, which has a direct application in traffic. I'll show you some examples of how basically this can be used. Okay, so OCR was targeted initially, and they came with sophisticated solutions for OCR. Okay, optical character recognition. So whatever you write it on a paper or you type it on a paper, after scanning you create an image, computer will be able to understand that. That solved a lot of problems also. I mean to say that a lot of documentations earlier were done on handwritten, or those documents which were available with the governments or many other agencies, they were not in good form. So we need to digitize them. So digitize one form can be just keep the image, but if you would like to do an text extraction from, you need OCR. So that's why OCR is an integral part of such a system. Now this application, face detection application, is very common. I mean to say that we saw it maybe 20 years back in those cameras. Today also we see these applications, maybe with some more enhanced features, like how many people are there, smiling is there, then maybe mood detection. I don't know. In these days, mobile cameras are pretty smart. Even the shutter can work with, depending on your smile. Smile shutter is there. Then the blink shutter can be there. There can be n number of such applications. Okay. These digital cameras, particularly the mobile phones with high definition cameras available, the softwares are pretty common, which can actually enhance the user experience. So essentially, this is a kind of enhancing the user experience. Yeah, we are more comfortable using these devices now because these devices are now more intelligent in a sense. They can take lesser amount of battery, they consume less amount of energy. Okay, and even hands-free operation is there. You don't need to click the button. You can even speak, it will understand. Okay, so all these features are getting included into these applications, into these systems, and that is essentially making them more users friendly. Okay. Face detection, we started with face detection. Now we have many other things. You point your mobile phone toward a particular direction in a famous place, it automatically brings information that where you are focusing based on your current location and based on the image currently being shown. It can also change the shooting mode depending on the objects which are available in the scene. So how it is working? So that means there is a AI engine, artificial intelligence engine, which is running, that automatically understands that what is the probable scene currently being observed by the camera, and accordingly it tries to adjust the lighting, it tries to adjust the camera parameters, the zoom factors and other things. So that is why we call it an intelligent systems of camera. Like smile detection, these are very common. Okay, but obviously it can be extended into many other applications also, like particularly for funny gaming applications also. Object recognition has other applications like in supermarkets. I'll show you other more practical applications which are being used. For example, this is one representative example where basically you can see in a typical shopping mall, your shopping cart contains all the objects, and if you have a camera installed there which can automatically identify that what are the objects placed, so it can automatically identify and it can create a bill, which will essentially expedite the process of bill generation and clearing the customers. Okay. So this is one application I'm showing. That there can be many such applications. Vision-based biometric. Okay, it's part of healthcare. I mean to say that it can be security, it can be used in security, it can be used in healthcare. In a security, I mean to say that in immigration, typical immigration part, you can actually use this vision-based biometric to identify that whether the person who is entering your country or exiting from the country has the DNA footprint or the iris footprint, which is as per the recorded database or not. Okay, so this particular example I am showing, this Afghan girl was identified by her iris patterns, and it became a story. So her iris pattern was matched the database, and finally her mother was found. So that is what it can actually provide. Obviously, the ease of using the devices. We have fingerprints, we have mouse, now we have face. So face locking passwords. Your system will automatically unlock when you sit in front of your system. So that is possible just because your system understands that this is the face. And the challenges, I'll tell you, there are challenges also. For example, instead to fool the system, if somebody intruder just grabs my photograph and print it and keeps it in front of the camera, whether it will recognize or not. Now that's what we call it That's what we call it, the intelligent system. So we actually, humans can differentiate that whether it's a person or it's a photograph of the person. So you can fool the computer if the computer is, or if you can fool the system, rather than not a computer, you can fool the AI system if the system is not properly trained. So even with face unlocking things, people may enter into your system with a photograph. So how do you come up with a more sophisticated, more accurate model that will not be fooled by such intruders? Okay. So that is what one challenge. Like another application is, this is basically used in augmented reality based applications. Find that you focus your camera toward something, a real life object, and it automatically fetches the description about the object. So it identifies it, and then it searches that where is this object, and maybe it brings lots of virtual content over the field of the view, and it helps you to identify that what is that object, what is the, I mean to say that this can be used in tourist places. And special effects, we have already seen these things, like starting from movies, Matrix to all these movies, motion pictures. We actually, take help of computer vision, 3D animations to enhance the visual experience. And sports, in a sense, particularly for sports analysis, we can do it. I'll show you some examples toward the end, that how basically, sports analysis, even these days also, you might have looked into these cricket matches where during the match itself, they actually do a lot of tasks. They provide the tracking of the ball. They also provide the swing information. They also provide the tracking of each and every player. So from a top view, you look into that, which player is standing where within the field. Okay, so lots of applications are there in sports also, and particularly I'm more interested in highlight generation. I mean, say a sporting event can go for more than 3 hours, 4 hours, like cricket match, which takes more than 3 hours, 4 hours, 7 hours in a whole day match. Okay, now we may not be having enough time to watch it. Why don't we automatically generate a summary of the match, like highlights? Okay, usually what we see that these broadcasting channels, they actually create highlights. Now you can actually generate highlights based on your choice. Okay, you can give a command like that. I want to only see when maybe Virat Kohli is batting. I do not want to see anything else. Okay, so it will automatically show you those portions of the match where he was batting, or maybe particular type of shot being played by XYZ player. So these sort of things are pretty much interesting. Google actually started a dream project in 2010 that's called Google Cars. They wanted to understand that how basically autonomous driving can be. Still, this is challenging. In a country like us where our transportation system is still not that advanced, particularly with the involvement of the pedestrians, then vehicles, then traffic police, and obviously domestic animals, okay, which are parts and parcel of our daily life. You can see that these objects or actors, they are actually present always in a typical on Indian roads. Okay. Now, how do we basically ensure that a car which is AI-enabled autonomous vehicle will be able to understand all the interactions between these objects, which may be easier to implement in a road segment in US where the traffic rules are very strict and people usually follow the traffic rules, which may not be correct in all contexts or in all countries. Okay, so even if they, not only Google, Tesla also came, many other car manufacturing companies, they are actually coming with good solutions, but no one is able to claim that this is going to be 100%, or a foolproof system which can run on any road. So it can be an assisted driving kind of thing, but it cannot be a complete, self-driving car. And then interactive games like Kinect and other things which are already available. I mean, so these are mainly used for gaming applications. Okay, particularly, the young generation are more interested to learn, gaming things. They want to learn, basics of physical exercise and other things. Okay, so that is what, where it can be also used. Okay, industrial part, which I was I'm more interested in basically doing, automation, because here the risk involved are this. Yes, in a sense, if you talk about the autonomous vehicle on an Indian road is more risky than doing some automating the industrial pipeline, because the damage will be covered in case of the system fails will be lesser, okay, in terms of human resource damage. Okay, and industrial areas can be more controlled environment, like you don't expect unknown or unnecessary objects coming into the pipeline or coming in front of the camera, so that helps. So that what is the environment, you don't expect that the environment is changing a lot. So that is the advantage of applying visual surveillance into the industrial applications, rather than going for fancy things like autonomous driving, something like that. I'm not saying that it's not going to come, but it will take time. But here, industrial applications, starting from small industrial applications, say a conveyor belt where the objects are moving one by one, a particular small object is moving. You can simply develop AI machine learning based systems to count the number of objects passing. That's not harmful. Okay, even if one of the objects is missed, it's not going to create a lot of problem in the system. Whereas in case of autonomous driver, if it wrongly identifies a pole as a human, it can do anything. Okay, so that is the problem. So when we talk about visual surveillance, if you ask me, my opinion is we rather go for more industrial applications than to directly go for traffic applications, particularly in autonomous driving. Medical imaging is one part where I feel that it has great chance. I mean to say, it is not replacing the doctors, but it will be helpful. It will be acting as assistive tools or technology for the doctors. So we do not want to replace the doctors. Rather, we want to help the doctors. Say, given a CT image or 3D MRI image, which may be large in dimension or in resolution, a doctor or an expert may not be able to zoom in to the specific location always. So you can actually, because if you look into these whole slide images, particularly those who actually do tissue culture, those whole slide images are huge size images. So one image can be of say a couple of gigabytes. Okay, so if you would like to open up an image and then try to focus each and every pixel, a doctor will not be able to do it, or a cancer specialist will not be able to do it. So why not to basically help the specialist by reducing the search space? So that is what I am talking about. They are not replacing. So we are not replacing the doctors. What we are trying to do, we are trying to help the doctor by basically reducing the search space. So that's why medical imaging has great potential. So that computer vision, visual surveillance has great potential. Now, switching to the next portion of the talk, that let's understand the basics of machine learning, how basically machine learning can help. Okay. So we want to develop algorithms that allow computers to learn. Okay. So in a particular lecture, what we'll see, we will rather use the narrow definitions. So we learn to assign an object or an example to one of the several pre-specified categories, because we are talking about computer vision or visual surveillance. So this is actually called pattern recognition. We want to recognize patterns and we want to assign these patterns. Okay. So for example, this is a face image. Whether it's a teacup, whether it's a face, whether it's a phone. Okay. Obviously, it's a face. So our objective is, given an object, we want to extract meaningful features, and there may be a set of labels given. We want to, probabilistically match the features or map the features with one of the labels, so that in most of the cases this mapping is correct. Okay. So face detection is one of the applications, ML applications, where you see that what are the objects? Objects are nothing but image patches, like those rectangular patches. The rectangular patches, which are square patches, which are shown, they are objects. Okay. Now, what are the labels or classes I was talking about? The label can be face, non-face. It can be a car. It can be a cow. It can be a blah blah blah. Anything it can be. Okay. So those are the labels. Okay. In medical, I was talking about objects are basically pixels, a group of pixels. The classes can be different types of tissues, like it can be stroma, it can be lumen, it can be other types of tissues. Okay. So these are classes. So how accurately we can map them, so that when we present them to the physician or the expert, the physician does not need to actually look into each and every object present. Okay, so basically it's an assistive system. ML has also applications in acoustics and speech. We will not go into the details of that part, but I just wanted to give you an idea that it is also used in other domains. Okay, so where the objects are acoustic signals, where the classes can be phonemes. For example, the sound which is on the left side, this is basically the acoustic signals, and it may lead to a sound which reads like "We are Indians." Okay. So that's why these are phonemes. Okay, we can have in economic applications, for example, where objects can be people, and the classes can be whether the loan can be approved or not based on their past data, maybe whether based on their income, their marital status, their debt, their age, blah blah blah, all these things, whether the loan can be approved or not. So ML can be applied. So we have seen that ML can be applied in many things, like we do it in vision based applications, we do it in medical imaging, we can do it in audio processing, we can do it in typical in the business applications. Now, natural language processing is one part where basically we can also apply ML, and which is a definitely different domain than visual surveillance. But why I'm especially giving one more slide here, that's because this is another one domain of research which requires a lot of understanding of machine learning, and machine learning has a lot to do for this particular domain. So here researchers try to develop computer models that can understand human language, natural language, and speak human language. So if we are able to do it, then computer should be much easier to use. Anyone can use it. If I am able to communicate with the computer with my mother tongue or local language instead of using a scientific programming language like C, Python, other thing, whatever I am writing, if the computer understands, probably that will be the best day. That's why it has great, potential. And many of these NLP approaches to NLP, they are particularly based on machine learning. So that's it all about the preliminary of the applications of machine learning. Now let us see that how basically machine learning can be, AI and machine learning can be applied to visual surveillance. So here, particularly, I will show you some applications and related theories that how basically AI and machine learning can be used for visual surveillance. I'll show you some examples, and we will discuss these topics with respect to some applications. So the first one is crowd tracking. Now, why I chose this crowd tracking? There is a reason. Because many of the surveillance applications, the primary objective of these applications are to identify people and track them. Now, when you would like to identify more people, or a group of people, it becomes crowd. It may be 5 people, it may be 500 people, it may be 5,000 people. So, one of the most challenging problems in today's world is how to manage crowd, particularly in dense scenarios. Okay. So that's why the applications of machine learning and AI, particularly for crowd surveillance, is very important. And that is what I will show you, that how basically it can be used. Let's take some examples like this. In India, all these gatherings are not in India, obviously. Some of these gatherings are in India. Okay. Particularly, you see the right side. We all know that this event is coming, Rath Yatra. Okay, where that lakhs of people are actually gathered, and obviously, you need to have good surveillance, which can understand that whether the crowd is actually going, unstable at some point of time. Similarly, other events like, a marathon or a political rally, okay, these are there, and such gatherings are not uncommon in a country like India because of our population density. Also, even if a small gathering is there, the number of people, we all often get too high and within a confined area. So it means it creates pressure within that area. Pressure in a sense that there will be randomness within the crowd. How do we basically identify that or understand that how the crowd is behaving? Now, what manual monitoring happens? Somebody is looking into the CCTV camera light on the left side. Okay, it requires precise human efforts. It is error prone and it is time consuming. So the three important points related to manual monitoring is that it requires precise human efforts. Somebody has to constantly watch into the CCTV things and understand that whether something is wrong or not. And we all humans, we are prone to errors. If we are asked to do one thing for a longer period, we may do mistakes. That's why it's error prone. It's also time consuming. If you have a large number of CCTV cameras, display systems are there, so finding out exact point, okay, maybe a time consuming thing. Whereas on the right side, if you look basically, if you go for a typical computer vision based monitoring, you will find that it requires lesser human efforts. Obviously human efforts are needed, but lesser. It does better information fusion. It can process high volumes of video at lesser time. It is prompt, accurate and intelligent. Now, accuracy is a subjective thing. I mean to say that you may argue that sometimes human observation is much more accurate. But if you are able to train the system properly, it will be more accurate than the typical human-based, systems. Okay, and it will obviously intelligent. Now, I'll show you one one framework where dense crowd characterization can be done using, simple physics-based rules. Okay, so in physics-based models for crowd dynamics, we can actually analyze the crowd with the help of conventional, physics-based theories. Okay, so crowd dynamics in terms of randomness and energy computed with the help of Gibbs entropy and kinetic energy can be done. The framework is something like this, where basically you take the video and you actually calculate the optical flow computations. Then you do some kind of quantization, orientation quantization direction wise, because you may have all 360-degree. You do not want all of them to be available. You just want some of them to be quantized. So you can have 8 levels, 16 levels, depending on the requirements. You do a lot, post processing kind of thing like connected component analysis. You find the groups, okay, and you calculate the energy and entropy of these groups, and you do the analysis. Okay. Now energy, again, you can have, kinetic energy, typical kinetic energy. Okay, and you take an average for the whole frame having n points. Okay, kinetic energy is basically, we all know that mv square. Okay, so assuming that here the mass is unit mass, because we are actually not calculating the energy of the moving particles, rather basically these are the points, key points where there is no mass. Okay, so with certain relaxations in the equations, we can always calculate the energy of the frame, and we can use it as a parameter to understand. Then also you can calculate entropy of the system. Okay, considering each connected component as a microscopic state, because this connected component means those are nearby people, nearby optical flow points. Okay, and the whole frame as a macroscopic state. So the entropy of the frame can be calculated using this, where I is the number of groups in a frame. Okay, and you actually find out the probability distributions of the dominant angle of the ith group in the frame, and you do the observation. Now I'll show you some examples of these two parameters, particularly entropy and energy, and let us see that how basically it varies for different types. So if you look into it on the video, we are actually showing one marathon video where people are moving more in a structured manner, even though the direction is varying. Those color points are basically representing, most of the time representing directions, because some of the people are moving in upward direction, some of the people are moving in downward direction, some of them in a vertical direction, horizontal direction, depending on their current position. So that's why you get different sort of color slots. However, what we can see that when we basically find the entropy, we find that it's a high entropy without much fluctuation, whereas the energy is low. Okay, and also it's a kind of stable. Now let us see that how it is basically for a crowd like Rath Yatra crowd, where you can see that entropy is varying a lot and energy is also varying a lot. So these variations actually provide us the type of the crowd that we are dealing with. Okay, this is a preliminary observation. Okay, now with these preliminary observations, we can actually come up with a more complex model or more accurate model, which may be a little bit complex in nature, to understand that how basically this crowd is behaving. Okay, so let us see that what are the observations from this particular experiment. So the observations, what we found that if significant fluctuations are observed in interframe energy, it can be attributed to a fast moving crowd with higher velocity. So again, these observations are particularly based on these parameters, entropy and energy. If you come up with some other physics based parameters, you can also come up with some certain other types of relations. Secondly, if the fluctuations in interframe energy differences are low, then the crowd can be assumed to be moving at a uniform but lesser velocity. The third observation, what he found, that more fluctuations in the entropy curve indicate varying randomness in the crowd, which was there in the Rath Yatra crowd. And for constant entropy, the randomness can be assumed to be less in a video. So with these observations, you can actually classify the crowd. Now, let's go into the some advanced part, that how we would like to now segment this crowd. Okay. So here, some of the researchers, they actually proposed here, this research work has been carried out. Whatever I'm presenting here, this has been research work carried out at IIT Bhubaneswar, some of our researchers. Okay. And also allied research works which are going on across the globe. I will show you parallelly how they're working. So we adopted physics-based model, like a typical Langevin equation-based model, which actually works on fluid. Okay. So we can see that with the dynamics of non-equilibrium systems can be represented with this equation, where the particles are all assumed to be Brownian particles, and they actually experience different types of forces. One is the random fluctuation force, which you can see in the green on the right side, the diagram. There is a random fluctuation force, which is shown in the green dotted line. The particle also experiences the Newtonian force, which is in the, obviously the Newtonian force is there, which is based on attraction, that is there in the central, which is the red part, and it also experiences the frictional force. That frictional force is because of the nearby particles when they are moving, so there will be frictional force. So with these three forces, the Langevin force model is established. We did a little bit of modification, okay, and we basically came up with a new formulation where the internal force is basically presented as a summation of external force with a drift as well as the disturbance. Disturbance is obviously coming from the environment disturbance. Okay, so the drift can be along x-axis, drift can be along y-axis. Okay, now with this, so we actually use this modified Langevin equation and applied it for segmentation. Now, how we have applied it? Now, if you would like to do optical flow calculation in each and every frame, it is a time-consuming process. Optical flow is a time-consuming process. What we did here, we applied optical flow at certain intervals. In between the interval frames, we predicted the positions of these pixels or group of pixels within the neighborhood with the help of this Langevin model. Assuming that obviously there are certain restrictions applied. We cannot assume that these particles act as fluid particles. That's why relaxations are there. But with certain relaxations, we are able to calculate their positions without going through the optical flow in each and every frame. So this particular framework, which actually talks about this, and these positions and velocity estimation, and from the velocity itself how the positions are estimated are given here. This has published recently in Pattern Recognition 2021. Okay, and you can actually find this paper itself. It's published by one of my PhD scholars. Okay, so it's an interesting work. You can look into that, how basically active Langevin force model can be used to predict segment the crowd, and the segmentation is not done by frame based on optical flow. Rather, it does segmentation at some point, and then it does prediction based on the active language enforced model. Okay, these are all details that how basically flow segmentation works. There is another paper also related to this one, which you will find it in expert systems with applications with the same research group here at Bhubane. Okay, they have also done an in a flow segmentation model. Okay, so where basically we wanted to understand that how the flow in the crowd is there, whether it is a stable flow, whether it is an unstable flow, whether it is a unidirectional flow, whether it's a bidirectional flow, okay, with certain relaxations. Okay. And we have also compared this with various other state-of-the-art algorithms. We found that the proposed method actually works better as compared to many of the existing methods. The results are evident here. So I didn't show you lots of curves and other things because unnecessarily it will take time, but you can look into those papers where you would find that how basically these systems are working. Now this was the research work which I was showing earlier, that basically talks about crowd flow in a dense scenario. Okay. Now, not necessarily that we want to apply surveillance on dense scenarios. There can be surveillance applications can be in an indoor scenario where sparse people are moving, or maybe we want to individually track persons. If you look into the example that I have discussed earlier, there we actually did not track individual people. We track a group of people as a segment, which may not be required in all cases, whereas we may require to track individual people, individual person. So that is what the next topic, so the next part in the discussion, I will come to the applications where object tracking, specific object tracking, and how it can be used for various visual surveillance applications. In a typical object tracking and application framework looks like this. You go into any research, computer vision, visual surveillance research domain, you'll find that they are mostly doing, similar thing. So this is a unified. I have tried to unify it so that you get a better understanding that how basically is there. So you have a CCTV camera, which detects key points, or you have a multi-object tracking where basically you track multiple objects. You extract the trajectories. So you create trajectory extraction and you create a database. You may not create a database also. You directly may use it, but you can create the database also. You extract features from these tracks. Then you do some applications, like you can do region of interest segmentation. You want to understand based on the movement of these people, which part of the scene is more important or more interesting. That is what you'd like to do. So that's the point number 3 here. Similarly, you want to do some abnormality detection. I'll show you that how the abnormality detection actually is. Then you can also do, or you want to do a kind of summarization and synopsis. This is also another interesting area. Summarization and synopsis, in a sense. Say you have been given videos for 24 hours recording. Okay. Now the problem here is that, are we comfortable with such long recordings? It may be meaningless for me to browse through all 24/7 days recording. Okay, it's a huge volume of data. I do not want to see the whole 7 days video and find out that where something wrong happened. So that is the 5th point, which is summarization and synopsis. It is really important in many of the surveillance applications. I will show you some of our research work and how people, the community, computer vision research community, what they're doing in the summarization part. Let's go to the basics of this motion trajectory, because all this research work from now onwards, what I'll be showing you to, they are mainly dependent on the trajectories and objects. So a trajectory is nothing but a path. So apply tracking to localize the objects in continuous video frames. You get the trajectories, and these trajectories are nicely defined like this, easily defined like the X, Y, and T, and you have a sequence like this: x1, y1, t1, x2, y2, t2, xn, yn, tn. So you have a trajectory of a moving object or even a stationary object for the t frames, t1 to t for n frames, t1 to tn. And what these x and y, they are telling that what is the position of the object during this time from t1 to tn. That is what actually it does. Okay, so it's a very simplistic representation, but with this we can solve a lot of problems. Okay. Let me tell you with an example. A trajectory, once you extract, if you try to visualize it in many ways, it can tell you, a lot of things. For example, on the left side, if I show you the trajectory in a 2D representation without giving the red rectangular bounding box, you don't get much information about the nature of the trajectory. As if the person started from, this location, as if the person started from this location and moved here and moved, or maybe started from this location and moved to this location. If I simply remove this, rectangular box. But surprisingly, if you put it in a 3D representation with time axis, it provides some valuable information. How? You can look into it. It tells that in z direction there were, for some time there was no movement in xy. It was only in z direction. It means the object was stationary at some point of time. So it means the path is not like a simple path that a person came from here to here. Actually, the person came here and the person waited for some time here, and then the person. So that information was not available in 2D, which is now available in 3D. So what I have shown you in the last slide is basically a depiction. Now there are certain challenges in the object tracking. You can face scenarios like occlusion. It can be scale. Some object is present very close to the camera, some object is present far away from the camera. It can be environment noise. Okay, I mean to say the lighting change, movement of the camera. You can have multiple objects moving. You need to track multiple objects. You can have fast moving objects, slow moving objects. You can have dense crowd. I have already, you have seen the examples earlier. There we did not track individual person. You can understand now that how difficult it will be to track individual person in a typical Rath Yatra video. It's very difficult to track individual people there. So dense crowd tracking is very. There are many other challenges. So we actually, there are many tracking algorithms, existing tracking algorithms. Here, basically, what I would like to show you that how different tracking algorithms actually perform. Okay, and how you can use basically kind of fusion strategy to come up with a better model. For example, this work proposed in soft compute in 2017 by one of my students. He actually carried out some experiments on using extracting the trajectories using existing algorithms and with respect to the ground truth, which is obviously manually tracking by humans. Okay, by manually locating the position of the object in each and every frame, which is a time-consuming job. And then we compared it, and we came up with a fused model, and which was giving better results as per the ground truth. Okay, this work can be found in soft compute 2017 paper. Okay, and also with this we are able to track the objects for longer duration. If you look into here, these tracks are long duration tracks. These tracks are long duration tracks. These long duration tracks are very difficult to achieve in surveillance videos. Why? I'll show you. If you look into this, is the KLT. Typical KLT is a very well-known tracker. If you look into this video, I hope that the video is playing. Okay, you can see that these tracks are lost after some time. You can't see these tracks for longer time because the tracks get lost in the process. So if this particular object moves to the top corner, okay, you want the whole track to be available. So that was not earlier possible with KL tracker kind of thing. Whereas with a bit of modifications, you can actually extract a long duration track like this just by applying heuristic. Okay, you are able to track this person even if the person actually goes in between various types of occlusions and also it's a long duration trajectory extraction, and it is quite accurate with the help of the heuristic that is proposed by Dr. Arif in soft computing paper. So the other way of can be you can apply grouping and tracking. So you detection of moving object using mixture of Gaussian and Hungarian algorithm can be used for to assign detection with a known track. Okay, and if a moving object remains undetected, positions can be predicted using predictors like a typical Kalman filter based prediction. I'll show you some of the samples sample outputs that how basically this tracking with a Kalman filter based prediction actually works in a challenging scenario. Why I'm saying this is a challenging scenario, this video has been recorded at IIT Bhubaneswar campus in a rainy day, cloudy rainy day. You can see that it was raining heavily, and basically fixed camera. We actually use the camera to record this, and you can see that these car trajectory, bike trajectory, they are pretty accurate even in the presence of environmental noise. Okay, so that is what actually it can do. If you basically do a bit of post processing with the help of filtering like Kalman filter to predict the position, you may not be able to recognize the object in each and every frame because it goes through occlusions. So why don't you basically then predict the positions? That is what it has been done. It may be easy for a scenario like this. This is a typical sunny day, okay, and objects are moving. You will be able to track them, but not necessarily always you will get scenarios like this. Now the other way of tracking is basically tracking by detection, where you basically do tracking by detecting the objects in individual frame. Now for detection you need a framework like this. This is a typical YOLO V3 architecture. Many of you are aware about this architecture. It's very popularly popular architecture for object detection. It has several convolution layers followed by dense layers. So you can actually train such an architecture for the objects of your interest. Okay, and actually we carried out several experiments with different versions of the YOLO, and we found that sometimes it is working good and sometimes it is also failing. Okay, so these failures are obviously due to lack of data in the training, but you can always change this by applying adequate number of samples. Now if you look into indoor tracking, here you will see that it is perfectly working, because the reason is that the environment is less noisy, camera is static, lesser number of objects, okay, and you get very good tracking. You can see that here basically tracking by detection, not only the humans, it can also even track the smaller objects, like this person is carrying handbags. Okay, so this is what detection based tracking can do. Actually it tracks as well as it detects the objects. Okay, so okay, okay, let's continue this. Yeah. So what I was showing earlier, basically, the 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 tracking which we actually, the performance which we have received within an indoor environment like this. You can see that the objects which are even smaller, maybe insignificant objects being carried by the persons, they are also being detected. So that's because that's a nice thing about this YOLO kind of architecture, which can actually detect different types of objects. Okay, but not necessarily that this will be always a good scenario like this. For example, this girl, she is speaking over a phone. It was able to recognize that there is a phone. Uh, we actually also we can review a paper like this. This is a recent work. This is ICIP 2017 paper by Nikolai et al. They actually proposed something, tracking based on simple online deep tracking. This is called SODT. If you look into the architecture, it's very simple. What they do it, basically you have a video, you have two frames, frame I and frame I plus 1. In individual videos, you detect these persons, okay, and you associate these detections, okay, with the label. So that association is very important. If you look into it, the detections are performed independently. In this frame number I plus 1 and in this frame number I, you detect two persons. Now the association logic, it tries to associate object number 20 of frame number I with object number 20 of frame number I plus 1. So that's why it gets a label 20. Similarly, it also tries to do for all other objects which are present in the frame. So that's why this object number 15 is getting labeled. So this, if you are interested to know more about this work, you can look into this paper. This is a nice paper. Okay, you can understand that how basically they are doing the association. These are all detection and tracking. They detect the object and then they associate. So in detection tracking, using single thing, we can do it. These white frames are basically ground truth and blue are the detection. You can see that it is quite accurate. Even it is able to detect multiple persons, with very good accuracy. SODT is able to detect it with very good accuracy. Sometimes it is failing because of occlusion. You see here we are not doing any kind of prediction. So that's why sometimes it is failing, but otherwise fairly it is working. Okay, even it actually works on public data sets. All the other videos earlier I have shown, they are basically IIT Bhubane data set, whereas this one, you basically see the performance in a typical outdoor MOT PETS 09, which is a publicly available popular video surveillance data set, where you can see that it is also working pretty nice, and object levels are maintained. And some other data set videos like this, it is pretty good. You can look into this, but these are all based on basically multi-object tracking based on SODT. Okay. Then came the next version of this deep adversarial deep tracking, where basically you apply ResNet as well as a convolution networks together in a framework to basically do the detection. So this is basically proposed by Zhao et al. It is in 2018 Siliphier paper, where you can see that this has this paper can actually detect and track the person very quickly. Okay. In adversarial deep tracking, actually initially it says convolution network is fine tuned by the frame level, so it is basically object level detection. In the next stage, RNet predicts the state of the target in the current frame by utilizing the target patch and the search patches. The search patches are usually extracted from and around the location of the target. So obviously you don't do the searching to in the whole image. That will unnecessarily take time. Okay. And lastly, the CNET performs the discrimination between the matches and finds the match that is closest to the template. This is used to predict the state of a target in the present frame. Now, whatever I have discussed so far, they are basically mainly supervised tracking. I mean to say that you train a system with some labeled data and then try to apply supervised learning for tracking. The next part, which is I will show you, this is another domain of unsupervised learning. We'll see that, but let us quickly understand that how it is different. In case of learning, we know that there are three types. It can be completely supervised, which means that the machine learning task for inferring a function from a labeled training data. Whereas in case of unsupervised, you don't have labeled data, you have unlabeled data. In case of semi-supervised, you have partially available. These are all preliminary things, you may be knowing it. Just for completion of the talk, I just included them. And we also have different types of models. We can have parametric models with a finite number of parameters, which has a finite number of parameters. We have non-parametric models where it grows, the number of parameters grows, okay, as the model evolves and with the amount of training data involved. Then we have processing model. We have models, we can be having offline methods, we can be have online methods. Typically, the entire learning framework can be discussed or categorized like this. You have supervised, where you have ANN, support vector machines, naive Bayes, now other classifiers. In case of unsupervised, we have Dirichlet process, which is a model. In case of semi-supervised, we have constant learning. Now let us look into, because I told you now this particular part of the talk, we will be concentrating more on the unsupervised part. You'll see that how basically unsupervised models have evolved over time. Particularly, I'll show you how basically these motif mixture based and Dirichlet process mixture based models are there. Okay. Now, in case of typical unsupervised model, what happens? We have this is a paper published by one of my PhD students, Dr. Santosh. He published a model that's called temporal unknown incremental cluster-based modeling, which is a probabilistic model based on Bayesian theory, and he was able to predict the position of, or it was basically based on the grouping of the pixels. So initially you apply optical flow, and then you get the response of the optical flow filter, and you try to group the pixels which are having a response above a threshold, certain threshold of the optical flow threshold, and then you try to group them. So with the probabilistic model, he was able to track pretty good, and you can see that I'm not going into the mathematical detail because this is too much mathematical. You may not be able to able to understand in the short span of time. Those who are interested, they can look into this paper, okay, where it is where he discussed about that how unsupervised model can be used basically for object tracking, and it actually performed better than the best. I mean to say that if you look at the KLT was not providing the actual track; it was breaking in between. Similarly, mean shift was good, but toward the end, mean shift was also fading. Whereas in case of TUIC, this is the paper I was talking about, IEEE Transactions on Intelligent Transportation System 2018 paper, where you can look into this, that how basically this object tracking, is perfect for scenarios like this. Okay. Now, so we have looked into supervised tracking, we have looked into unsupervised tracking, and we have seen that what are the challenges and what are the possibilities. Okay. Now let's apply this tracking for some application, for some real life applications. I'll show you. The first one is the tracking for visual synopsis. So if you look into this particular depiction, that there was a person who moved from one location to other location. In between, the person was staying for some time. Okay, I was showing a similar trajectory earlier, where basically we were trying to understand that whether this trajectory was from the start point to the end point, and in between there was the person was standing for some time. We could not visualize it in two-dimensional representation. Whereas when we went to the three-dimensional representation, we could actually see that how the person actually spent time in a particular place. Okay, so that is what we will look into it. How basically trajectory can be used for summarization. So what do we mean by trajectory-based summarization? We would like to summarize the video or long duration video. Summarize means we will shorten the video based on the behavior of the object. Okay, so that is what basically we call it trajectory guided summarization and synopsis. So the work which is being shown here, it has been published in PAMI, Pattern Analysis Machine Intelligence by Rich et al. In 2000 in 2008. You can see, go through that paper. They are basically what they try to do. They basically, try to summarize the objects, okay, within a short duration, objects and their movements within a short duration. But in doing that, we have found that their results actually, even the similar object may be appearing more than once, which is not basically a good thing. You can see that this particular lady is appearing 2 times in the same frame, which is not physically or practically possible. Similarly, the same person is appearing 2 times in the same frame. So when they actually stitched these tubes, they call it tubes. So as the tubes belong to 2 different tube ID in optimization step, they may put together in same frame, resulting confusing synopsis. Okay, so that's why this is a confusing synopsis. So we can actually come up with a better architecture for generating the synopsis, where I'll show you with some examples that how basically this particular algorithm works. The initial part, we do background extraction, object detection, object segmentation, object tracking object, and extraction of tube. All these components we have already looked into it, and we create the object database. We group the tubes. This grouping of the tube can be done based on the objects type, based on their movement patterns, and this grouping can be done in many ways. And then we actually apply some optimization. It's a multi-objective optimization to generate the synopsis, because synopsis is something which you want. Say you have a 1 hour video, you do not want the synopsis to be 50-minute synopsis, then it has no meaning. Obviously you want to have a synopsis which is maybe 2 minutes, 3 minute synopsis. At the same time, you do not want the synopsis to miss important events. Now if there are so many important events and you want to accommodate them within a small duration, then you require better optimization techniques. That's why this is spatio-temporal optimization of placing the object trajectories over a limited number of frames. That's why it is challenging. Okay, I'll show you that this is an architecture which we actually proposed for different types of applications. Okay, but essentially we wanted to generate the synopsis. Okay, but the synopsis will be also generated based on certain query. I'll show you with some examples that how it is working. Let us take this particular framework where we have used a typical object classifier with 3 types of objects. These objects are nothing but cars, 2-wheelers, and pedestrians or humans. Okay, something very simple. So we have basically designed a classifier which is a very simplistic classifier. We did not use a complex YOLO V3 model, because that model itself is a heavy model. We wanted to test it on a simple system. So why I am showing this, people who are interested to work, they can actually design their own network depending on the application. Why to unnecessarily take a completely trained YOLO framework which can recognize thousands of types of objects which may not be required. That's why I told you, in industrial applications, you know that what are the objects you are going to see. Why unnecessarily to design a classifier that can classify thousands of objects? It is not needed, because that environment is a controlled environment. So here, for this particular application, we chose 3 types. One is car, bike, and pedestrian. You can look into these 3 types of objects. In IEEE transaction and intelligent transportation systems, you can again look into this paper from our website. So you can look into this. This is a one master synopsis of a 1 hour video. So this times what it shows that when these objects were present in the video. So you can see that an object is present at 8:36 a.m. Okay. So at the beginning you can see that these three objects, this object was present, this object actually passed during the time 8:15. This object passed during 8:02. This object passed during 8:10. But they are all being shown at the same time. How it is possible? Because we have individually detected these objects and extracted their tubes, and we proposed a spatiotemporal optimization to place these tubes so that there is no ambiguity. It's not like that one object is moving over another object, which was not possible in the method that was proposed, that was I was showing earlier. Okay, that paper. So we actually did a kind of optimization here, and we were able to generate meaningful synopsis. Okay, what I mean to say is meaningful synopsis. Synopsis should be meaningful, even though it has some glitches. Actually 41 seconds. It's 41-second video. So what it tells that within this 41 second, I can actually express all the objects which moved within this scene during the last 1 hour. So if I create a video like this, I do not want an inspector to look into the entire 1 hour. The inspector can only look into this 1 minute video or 40-second video and take a decision. Okay, that was the objective. Now I'll tell you that I want a better solution. I only want to see the object synopsis which are based on car. So this is another synopsis. Obviously the bus is coming because we have categorized this bus as a car, or we have trained this as a car. So you can look into it. It will only show the objects which are of type bus or car. Okay. It will not show you any other objects, or try not to show. Even if it shows, it may be a false positive. Okay. But most of the time you will find that this is only showing cars. Okay. And this has also application. Somebody may want to say that I want to see all the red cars passed during the period 8 a.m. to 11 a.m. from this gate to that gate. A query, textual query can be something like this, and you generate a video for the last 24 hours. Okay, so that is one application. So when we actually, how further, I mean to say that if you would like to make it more complex, or a scenario is a little bit more complex, you can actually give a more specific query. For example, here we understood the paths. We found that there are 3 different entry regions and exit regions: this blue region, this red region, and then green regions. And we know that we understood that what are the different possible paths from the trajectory itself. We found that the paths are mainly like this: entry blue, exit blue, entry green, exit green, entry red. Okay, so this way we actually, and then green to blue, blue to red, green to blue, or blue to green. So these are all possible combinations. Okay, now let us see that how can we make a complex thing. So if you give a query something like this, now this is more interesting. We want to see all the objects which have moved during 8 a.m. to 9 a.m. from green region to blue region. It will only show you the objects which have moved. From the same video, it is automatically generated. These videos are automatically generated. The synopsis video, it's not a 1 hour video. Again, it's a 1 minute 15-second video. You will only see the objects which are moving from this region toward the right side. You will not see any other object. Even if it comes 1, 2, they are false positive. Obviously no system is fully 100% correct. Since ours also, it's not 100% correct, but we were able to achieve much better result as compared to other methods. I am not showing you the comparative performance actually. In the paper, actually, we have presented everything there itself. You can look into those papers, but they are basically we are able to do. But why we require it? Because essentially our objective is to do something like this. It's video to text. So given a video, okay, we want to actually generate the textual description of the video. So that is the ultimate objective of a surveillance application. You have been given a video, you'd like to generate that what is the typical textual description of the video. Okay, like something like this. If you basically play like this, it's my textual description. I just give an example. It can be Dhoni finishes in his own way. But fine. Okay. So ultimate objective is we would like to generate textual representations, something like this. Okay. Some of the textual descriptions can be like this. Okay, like a white van coming from college building towards the residential zone, something like that. Okay. Now I'll finish it with a couple of applications shown on the traffic part. Here basically how the same thing can be applied. Basically we want to understand the traffic. We want to see that whether a particular car is violating red signal, or whether a car is over speeding, whether a car is smashing another car or not. So all these kind of research work can be carried out once you are able to track these vehicles, once you are able to identify these vehicles, once you are able to analyze their trajectories. Okay, like this is another paper which is a very complex mathematical model presented by one of my research scholars, Santosh. He published it in IEEE Transactions on Cybernetics, where basically he explained that in a crowded environment also, how can we basically understand the dynamic of the scene based on the movement of the people. So if you are interested, you can look into this paper. This is a bit technical in nature, but those who are interested, they can go through this paper. Okay. And the last is basically tracking for visual anomaly. Visual anomaly in a sense that it can be traffic accidents, it can be wrong U-turn, it can be overspeeding, it can be signal breaking. There can be different types of anomalies also. So I'll show you some of the anomalies. For example, this is a video. I'll finish this presentation today with this video itself. You can see that what we actually can do. This is an accident detection thing. You can see that we are able to detect the accident with the help of heat maps. You see the heat map is generated and the description will come at the end. Then the next scenario. We have taken this from publicly available data sets and we have applied our method. And you can see that the accidents are spotted and description comes also. These are all automatically done. Okay. So descriptions also involve how many objects are involved, what are the type of the object, what is the area of the accident, all these things are there. Now, if you look into this is the final slide. So if you look into that, how such applications can be developed, it requires object detection, it requires object tracking, it requires object interactions, and then obviously you need to process them appropriately so that you can take a decision. So at the back end, there are several machine learning and deep learning models which are running so that we are able to generate the spatial location of the accident, which is on the top left, then probable heat map, that affected area during that frame level heat map if you look into the top right, then the bottom left is consolidated heat map. The accident happened during 20 frames. So what is the consolidated heat map? And the final one is what can be a possible descriptions. So it says that the duration of the accident was 10 frames. The number of objects involved 3, and it found that in this accident 2 cars were involved and 1 motorcycle was involved, and based on certain heuristic it also finds that 28% of the entire scene was involved. So you can actually estimate the damage caused, during the accident. So this is one of the applications which is which I wanted to show it to you, so that you can also think about that several such other applications possible with the help of such techniques. So with this, I shall stop discussion today. Now it is open for your comments and discussion.
Thank you so much, sir, for making this vital subject so much easygoing for our participants. Anybody facing any doubt can please share their queries in the chat box so that staff can clearly clear them now. Anybody have any doubt?
I think there are some questions in the chat box. I can see somebody put a question that how without a thermal camera heat map can be generated. No, these heat maps are generated not using thermal camera. They are basically heat maps of the features. So we extract the features using deep learning framework, and then we basically generate these heat maps. They are not thermal camera based heat maps. These heat maps are technical heat maps. They are generated from the some of the last layer outputs of the classifier.
Do we have more questions? Okay, no doubt. The talk was slightly engaging, educative, and fulfilling because of your efforts, sir. These images you included in the presentation were obviously sweet and helped to understand the topic very clearly. Though it was a very small session as compared to the vast scope and utility of the topic, I hope all must have gathered a clear overview of the subject. So, thank you again, sir. Thank you so much.
Yeah, thank you. Thank you all for listening to this lecture. Thank you.
So we have reached the end of day one of Optical's online FTB 2021. I'd like to thank all of our participants for being so patient with us. We are really grateful to the guests, faculty members, and the whole team for their dedicated efforts. Before ending the session, let me brief you about tomorrow's program. Tomorrow we'll have three technical sessions. The first topic is cybersecurity, energy, and intelligence reduction in IoT. Second one is geospatial intelligence, and the third one is case studies of artificial intelligence and machine learning. All of the topics are quite interesting, including their respective speakers who will come from Texas University, USA, DRDO Bangalore, etc. The session will begin from 9 a.m. start, so please join before time. That's all for today. Thank you and have a great time ahead. Thank you all.
Thank you.